If you have 5 letters and 4 mailboxes, one of those slots is going to receive 2 or more letters. It is a physical certainty. No clever sorting algorithm or rearrangement of the mail can bypass this constraint. 5 objects and 4 containers means you are mathematically forced to have a double up. This is known as the Pigeonhole Principle. Its classical definition is simple. If you have n+1 pigeons and only n pigeonholes, at least one hole must contain at least 2 pigeons. The proof is remarkably brief. Suppose every hole has at most 1 pigeon. That would mean you have a maximum of n pigeons. But since we started with n+1, we've reached a contradiction. The extra pigeon has to go somewhere. This likely feels too obvious to be considered a profound theorem. It's so trivial you might feel embarrassed even calling it mathematics. But the power of this principle doesn't lie in the rule itself. It comes from the creative act of deciding what the pigeons are and what the holes should be. Choosing what to count and where to put it is what allows this triviality to resolve complex problems. We can see this in the birthday problem. If we treat 365 calendar days as the holes and people as the pigeons, it takes exactly 366 people to guarantee a collision. With 365, it's possible everyone has a unique birthday, but add one more person than there are days, and a shared birthday becomes a mathematical certainty. In 1842, Peter Gustav Lejeune Dirichlet used this logic to solve a problem in number theory. How accurately can we approximate an irrational number? Numbers like the square root of 2 have decimals that never end and never repeat, making them notoriously difficult to pin down with fractions. Dirichlet wanted to prove that for any irrational number, you can find infinitely many fractions, p over q, that sit within a hyper-tight tolerance. Specifically, the difference between the number and the fraction must be less than 1 over q squared. To prove this using mailboxes, we first pick a positive integer, big Q. Then we generate a list of numbers by multiplying the square root of 2 by every integer from 0 up to q. From that list of q plus 1 numbers, we throw away the whole number parts and keep only the decimals. These strings of digits are our pigeons. Every decimal part lives somewhere between 0 and 1. We divide that space into q equals subintervals, each with a width of 1 over q. These are the holes. Since we have q plus 1 decimal parts and only q intervals, the pigeonhole principle dictates a collision. Q distinct decimals are forced to land in the same subinterval. The consequence of this collision is that the distance between those two decimals cannot be larger than the subinterval they share. They must be within 1 over q of each other. The logic is simple. If 2 fractional parts differ by less than 1 over q, their original numbers are also close to a whole number difference. By subtracting those 2 original multiples, we get a new integer multiple, little q, that is within that 1 over q distance of some whole number, p. Because little q is at most big Q, dividing that error through means the difference between the square root of 2 and the fraction p over q is actually less than 1 over q times big Q. This forces the final value into that tight 1 over q squared tolerance zone we were looking for. Since big Q was arbitrary, we can repeat this for any value, producing an infinite sequence of rational fractions that get closer and closer to the square root of 2. By simply defining decimals as pigeons and intervals as holes, a counting rule for mailboxes just mapped the infinite complexity of irrational numbers. There is a generalized version of this principle as well. If you have more than k times n objects, you are guaranteed not just a pair, but a triple or a quadruple of collisions. This generalization is central to computer science. It explains why hash collisions are inevitable in large databases. Hashing maps a massive universe of data keys into a fixed-size table. Once the number of data points exceeds the number of available slots in that table, the pigeonhole principle makes overlapping data a mathematical certainty. Dirichlet's theorem and modern database systems are highly sophisticated subjects, yet they both rely on the same underlying logic. If you have more things than places, something has to share. The 5 letters and 4 mailboxes we started with represent a hard limit on how information can be packed. This same logic forces irrational numbers to have precise approximations and requires hidden patterns to appear in random sequences. The principle requires structure to emerge in every system. In any long enough sequence of numbers, for instance, A subset that is either strictly increasing or strictly decreasing must eventually emerge. These hidden patterns are mathematically required. The most obvious observations often govern the deepest ideas in mathematics. Inescapable order is everywhere, provided you have the creativity to see where the pigeons are hiding.